Welcome back to Next Up. Today we're going to have a look at another machine learning question commonly asked in interview questions. And that question pertains to what is regularization? Why do we use it? And can you give some examples of common methods? So yeah, regularization also kind of pertains to the whole aspect of cursive dimensionality that we tackled in a different video. And also it pertains somewhat to bias and variance, specifically variance when you have like one outlier reigning in into your modeling of the problem. And regularization can exactly help in those cases. With that said, let's have a look at the deep dive. It comes today from Analytics video. Learn everything about analytics. And this website also gives you a broad overview about different techniques. And as they advertise already on the headline, they provide Python keras code. We're not going to have a look at the code themselves, but we are going to go through at least some of the very basic regularization techniques that we should know before going into an interview. Okay, most of the common problems they say here is avoiding overfitting. Overfitting can be basically translated to variance. And let's have a look here. Avoiding overfitting can single-handedly improve our model's performance. You don't say. In this article, we will understand the concept of overfitting and how regularization helps overcoming the same problem. So they go on starting what is regularization. It helps into determining the just right factor, basically, on how to best model your function towards your data, right? And in those graphs, basically, you can see that clearly on the right-hand side, you have like a way to varying model. And on the left-hand side, you have like this model that's just biased to like drawing a line. And it all basically comes down to like the fact where you want to have like this peak point here where you get like a minimal error in the test set. But if you just continue to train and optimize on your training set such that you can get like a better and better error, you might end up actually getting a worse error in the test set, right? Because you probably have just overfitted on certain aspects. Same goes for like a network that is just too complex. So what can we do? Of course, we want to avoid overfitting, and we want to keep our neural networks at just the right amount of neurons and connections. So in machine learning, you will have a fair idea that regularization penalizes the coefficients. In deep learning, it penalizes the weight matrices of the nodes. So it's like two different aspects. That's basically two different aspects of the same problem that we want to solve. So we want to actually find a fitting where the line basically has a nice distinction between one data set and the other data set, and those two outliers here don't really reign into the modeling. And in order to achieve this, the two most common techniques to do so are L2 and L1 regularization. So here, most common types of regularization. These update the general cost function by adding another term known as the regularization term. So cost function is loss plus regularization term, which in the community for optimization and numerical optimization that's been around in mathematics for decades is like basically a standard term that they have used already all the time, right? So here it basically just gets like a machine learning or deep learning flavor. So how do they differ? So in L2, we see here that the term has a square. So we take, like we do a sum over our weights or sum over our errors and square that thing. we square our absolute value. And in L1, we just take the absolute value. We're just like basically it can be geometrically motivated, but here we basically just leave it at the fact that we square the error and here we don't square the error. And lambda at the beginning of the term here is the regularization parameter. So in L2, the weights may be reduced to 0. Like unlike in L2, the weights may be reduced to 0. And in L1, we are able to penalize the absolute value of the base. So they say here, it is very useful when we are trying to compress our model to use L1. Otherwise, we prefer L2 over it. So that's something that can be achieved. And here they also put like a very simple way of phrasing that in Python. And the third most important model to actually use regularization, here specifically in the context of deep neural networks, is that we use dropout. So dropout randomly selects some nodes and removes them along with the incoming and outgoing connections. Like as if you were to have like a graph and you remove one vertex of the graph, meaning that all its edges of the graph were removed too. Or if you are into like 3D modeling, you have a mesh and then you remove a vertex from that mesh, you will also have to remove all the faces and all the adjacent edges to it. So it's like kind of the analogy here. And they do that randomly. And they say it can be basically thought of as an ensemble technique in machine learning. And ensemble usually perform better on a single model as they capture more randomness, they say. So dropout is basically like a way to just double check which neurons actually really do the work, and which neurons basically just slide along values. So they say dropout is usually preferred when we have a large neural network structure in order to introduce more randomness. And again, it comes with a snippet for Python Keras how to drop out. And another aspect on just like going down into one specific route of fitting your model to your limited data set is to augment the data set. And that augmentation can be thought of just like taking the data that you have and altering it in a appropriate way, or in a way that you can conceive might actually be encountered in the real world when you later look at it. So here, for example, you've got shift, another shift, shear it along one axis, or shift and scale, and rotate and scale. Early stopping, we basically look at our training stage, and then just at that stage of the training, we perform with a validation set, so a set that's not included in the training, and see how we're actually failing, how well are we actually doing with the testing error that we expect on a real data set. And if we are actually like close to the trough with our validation set, we know we should just do an early stop and don't continue to go any further. So that already gives us the 4 most common techniques, and then just further down the road we just go through a lot of practical examples using Python and Keras that should not that issue, but instead we should just go back to the original question and see how can we concisely answer that in 2 or 3 sentences, and then, if necessary, back this up with follow-up answers if the interviewer has more questions on that. And so what do we do? What do we do with regularization? Why do we use it? And give some examples. L2 norm and L1 norm. Here they are listed with some of their more favorite nicknames called Lasso and Rich. A one-liner on why we do that, like we discourages learning a more flexible model to avoid the risk of overfitting. And then here it comes with some advantages and disadvantages. Rich L2 norm is model interpretability. It will shrink the coefficients for least important predictors very close to 0. But it will never make them exactly 0. So in other words, the final model will include all predictors. Versus in lasso, you can actually go all the way to 0. And this way you can basically sparsify your model. And then we had a look at two other approaches. One approach was the dropout, like randomly select nodes in your network and then just remove them with all their edges. And the other one was data augmentation. Take your data and then shift, shear, rescale, flip, whatever operation comes to mind, apply it to them, and add that to your data set in order to augment and enhance the data that we have in there.